All right, so far we've been treating work as an abstract mathematical quantity. Uh, Using the work kinetic energy theorem, it's possible to understand the physical significance of work. So what was the work kinetic energy theorem? It just says that the uh, net work done on a system is equal to the change of kinetic energy. All right, so for simplicity, just assume that there is one force acting on the system, right? So if this force does positive work, then W net will be positive and the delta K will also be positive, and that would mean that the kinetic energy of the system increased by the same amount as the work done, right? The same number of joules. And if the work does negative, if the force does negative work, then the kinetic energy of the system will decrease by that same amount. And so from there, you can conclude that the work done on a system by a force, what does it represent? It simply represents the amount of energy transferred to the system or removed from the system by that force. So if the force does 5 joules of positive work, that means 5 joules of energy have been transferred to the system, and the energy of the total energy budget of the system went up by 5 joules. And if the work done was, say, negative 10 joules, that means 10 joules of kinetic energy have been taken out from the system, right? So work done simply represents the amount of energy transferred to the system or removed from the system by the forces acting on the system. All right, so the next topic that we are going to discuss is potential energy. Okay, consider this situation. Suppose you have a box that's sitting on a rough surface. Here's the box. And let's say that you apply a force F on the box and you slide the box against the rough surface and move it from here to here. All right, the box started at rest and also ended at rest. And so let's say that the work done by you equals 100 joules. So suppose you calculated the work and you saw that you did 100 joules of work. Now, what is the work done by friction? Can you tell me what is the work done by friction? You can easily figure that out from the work kinetic energy theorem, which says that the net work equals the change of kinetic energy. Let me just switch to uh, Word so that I have more space to write. So anyway, so here is um, here is the box, and you applied a force F on the box and moved the box from here to here. And we just said that you did work done by you, work done by you is 100 joules. My question was, what is the work done by friction? The answer is, it has to be negative 100 joules. Why? Because we know that the box started at rest and stopped and also stopped. So it had zero velocity to begin with and zero velocity at the end of you pushing. So the change in kinetic energy is zero. And so according to the work kinetic energy theorem, W net equals zero. And that means that net work means the work done by you plus the work done by friction has to be equal to zero. And so that tells you that the work done by friction has to be negative 100 joules. Now, let us try to uh, physically understand what these things mean. So what does it mean to say that you did 100 joules of work? In the previous slide, we talked about the physical significance of work. So work done by a force on a system simply signifies how many joules of energy was supplied to the system. So you supplied 100 joules of energy to this system, which is the box, right? Where did that 100 joules of energy come from? That energy was stored in your body in chemical form, in various chemical forms, glycogen, fat, stuff like that. So, and then using ATP, you were able to convert that energy from chemical form into the kinetic energy of the box, right? So that 100 joules of energy it came from you. It was supplied by you. All right. What does it mean to say that friction did negative 100 joules of work? So we talked about how negative work simply means that the force is removing energy from the system, right? So what's happening here? You supplied 100 joules of energy to the system, and friction took away or subtracted 100 joules of energy from the system, right? And so in the end, the box has no net energy. Its kinetic energy has not changed. It was zero to start with. End of the process, it's still zero. So that is what's really going on. So you're supplying 100 joules of energy to the system. If there were no friction, then the system would have kept that 100 joules of energy, and it would have had 100 joules of kinetic energy if it was sitting on a frictionless surface. But the friction did negative work on it. And so as a result of that, the 100 joules supplied by you was taken away from the system by friction, and so the box ended up with no net change in kinetic energy. All right. Now, what does it mean to say that friction took away the energy from the system? Like, where did that energy go? Energy is a real physical thing. So if it's been taken away from the system, then it must show up somewhere else. So where did that energy go? Can you think of where that energy went? The answer is that energy was converted into heat. So while you were doing negative work against friction, heat was generated, and so the negative work done by friction just represents the energy getting converted into heat, and that energy is transferred to the air molecules in the room. So there's a very slight change in temperature of the room, um, and so that energy is not recoverable anymore. It's just completely gone, right? Okay, so that's a very, very important point. The energy that uh, when you did work against the non-conservative force of friction, the energy that you spent is just gone forever. Suppose you have buyer's remorse. So you've moved the box from here to here, and you are suddenly very unhappy with what you have accomplished with the 100 joules of energy that you spent. Is there any way that you can get that 100 joules of energy back? The answer is absolutely not, because that energy has been converted to heat, and it is now manifest in the slight change in the motion of the air molecules. They're vibrating slightly faster because they've acquired some energy uh, in the form of heat. So that energy is just gone. There is no way that you can get it back, right? So work done against a conservative force is not recoverable. So that energy is just completely gone, right? Now, let's consider a slightly different situation. Work done against a non-conservative force is what I mean, like friction. All right, now let's consider a slightly different situation. Suppose the box is sitting over here on the ground as usual, but this time you lift the box up. So you lift the box up from here to here, maybe, right? And let's say that you again do 100 joules of work, right? So if you calculate the work done by your force, let's say it comes to 100 joules, right? Um, the box does not have any. The box is again at rest at the top position, so there is no change of kinetic energy. So that means the net work on the box is zero. What was the force that did negative work on the box? The correct answer is obviously gravity. So gravity was pulling down on the box the entire time. And so gravity in this case did negative work as the box was lifted from the lower position to the higher position. All right, so you did 100 joules of work, and gravity did negative 100 joules of work, which means in this case, you did work against gravity, right? All right, there is a crucial difference between doing work against a non-conservative force like friction and a conservative force like gravity. In this second case, if you had buyer's remorse again, like you spent 100 joules of energy to lift this box up, and you're not happy with what you accomplished with your 100 joules, and let's say that you want your 100 joules back, right? In this case, it is possible to get 100 joules of energy back. You will not be able to get it in the form of ATP as it was in your body before you lifted the box, but you can certainly get it back in other forms, in a variety of other forms. What are the different ways in which you can get this energy, or how can you get this energy back? How can you get this 100 joules of energy back? Well, the easiest answer is, suppose you were to just drop the box, right? If you drop the box, it would fall from the height, and just before it hit the ground, how much energy do you think it would have? It would have exactly 100 joules of energy, right? If the box were made of metal and you made the box fall through a magnetic field, as you'll see in physics 2, it's possible to uh, get some of that energy back in the form of electric current. And using electric currents, you can light light bulbs, or you can play sound. So you can get the energy back in a variety of different forms, not just kinetic energy. You can get it back in the form of heat, you can get it back in the form of electricity, and so on, light, sound, whatever you want. So the energy that you spent, the 100 joules of energy that you spent in doing work against a conservative force, is recoverable. And that is the crucial point here. So the work done against a conservative force is recoverable, whereas that done against a non-conservative force is not recoverable, right? Okay, so hopefully that's clear. So doing work against a conservative force is not quite the same as doing work against a non-conservative force. When work is done on an object against a conservative force, the energy spent is not quite lost. And we say that the energy that you spent, like in that second case when you were lifting up the box, the energy that you spent can be thought of as being converted into a different kind of energy, which we call potential energy, right? So the 100 joules of energy that I spent in lifting up the box, basically, I stored that energy. I mean, that energy was stored in a new form of energy called potential energy. So potential energy can be thought of as stored work in the sense that it can be recovered and converted into other forms of energy anytime. So please make sure you understand what potential energy is. So the question of potential energy only arises when you're doing work against a conservative force. So if you do work against a conservative force, then the energy that you're spending in doing the work is stored in the form of potential energy. And you can recover that energy whenever you want in a variety of different forms. On the other hand, if you do work against a non-conservative force like friction or air resistance, then the energy that you're spending just goes into heat and it's not possible to recover it anymore. So there's no question of potential energy there. So that is what potential energy is. When you do work against a conservative force, the energy that you're spending is stored as potential energy. All right. So the work done against a conservative force leads to a gain in potential energy, right? So please keep that in mind. In the simple gravitational example that we looked at, we were lifting an object from here to here, right? So let's think through this carefully. So the force that I am applying in lifting the object, F, is upwards, obviously, and the gravitational force on the object is downwards. So I am doing positive work in lifting up the object. Gravity is doing negative work. So the gravity is our conservative force here. So when the work done when the work done by gravity is negative, then the potential energy of the system increases. And as a result of that, the object has a higher potential energy at the greater height. What would happen if I just let this object drop from the upper position? So in that case, as it's falling, will gravity do positive or negative work? The answer is gravity will do positive work, because as it's falling, the gravitational force is downwards and the displacement is also in the downward direction. And so gravity does positive work. And if gravity does positive work, then according to my statement over here, the potential energy will decrease. So this statement is summarized by this little very simple looking equation. And this equation is very, very, very important for your understanding of this whole subject. And this equation is also very important in physics too as well. So this equation says that the work done by a conservative force and the change in potential energy delta U are related by this little equation. So in particular, they're related by a negative sign. So the work done by a conservative force is negative of the change of potential energy. So please make sure you are fully clear about this equation. And if you ever get confused about this, you can always use the gravitational analogy to help this straighten this in your mind. So when you lift an object, you know that the potential energy increases, and in the process of lifting it, did the conservative force gravity do positive or negative work? The answer is it did negative work when you were lifting the object, right? So negative work done by the conservative force would lead to a gain of potential energy, and positive work done by the conservative force, that would be the case if you drop the object, would lead to a loss of potential energy. And these two statements are summarized by WC is equal to minus delta U. So this equation is so important that I've made this into its own slide. So please make sure that you're absolutely clear about this equation. This equation is also considered the definition of potential energy. All right. Okay, so I'm going to discuss this question in class. So you can give this a try yourself and see if you can come up with an answer. The only thing that you need to know here is that there are two things that you need to know for this question. One is that electron is negatively charged, which you probably knew already. And so negative charges are attracted to positive charges, as you know. And the force of attraction there, it's called the electrostatic force, is conservative force. Just like gravity and the spring force are conservative forces, force of attraction there is a conservative force. So keeping these two facts in mind and using this equation, see if you can answer this question. All right. All right, so now we're going to use the very important equation that we just developed. WC is equal to minus delta U. We're going to use that to come up with two extremely important formulas, which we're going to use throughout the course. So we're going to calculate the potential energy associated with each of the two conservative forces that we have in physics 1. So one of them is the force of gravity, and the other one is the spring force. So let's talk about the potential energy associated with the spring force. All right. So my Word document is frozen. Okay, so what we've seen so far is that potential energy is defined through this equation. The work done by a conservative force is negative of the change of potential energy. Now, what we're going to do now is calculate the potential energy associated with the spring force. In particular, suppose I've got a spring like this, and the end of the spring is currently at x equals 0 as usual. And suppose I stretch the spring out to some final x, and I'm going to call this x, and this was where x equals 0 was. And I want to see what is the change of potential energy of the spring, right? So this is sometimes called spring potential energy. Okay, so we can very easily calculate the change in potential energy of the spring, which is just delta U, from the definition of potential energy. So delta U for the spring is equal to the change in potential energy is equal to, from our equation there, is negative of the work done by the conservative force, right? So we need to know how much work is done by the spring force as the spring is stretched from x equals 0 to x final. This is something that we have already worked out in a lot of detail. It was on one of the slides, and in fact, I discussed it in the video prior to this one. So we saw that the answer to this was just minus half k x squared. Remember, we did the example where the spring was stretched from xi to x final, and then we also did a special case where x initial was 0, x final is just x, which is what we're looking at here. And the answer came out to half kx squared, negative half kx squared. So if you just plug that in, you get the answer to the change of potential energy is just positive half kx squared. This is called the expression for spring potential energy. Right? And typically, so this is giving us the difference in potential energies between this configuration, the unstretched configuration, and this configuration where the spring has been stretched. Typically, what we do is we assume that the potential energy is 0 when the spring is unstretched. I'll just write this over here. We assume that the potential energy is 0 when the spring is unstretched. So delta U typically means U final minus U initial, right? So U initial in this case was 0 because the spring was unstretched. And so delta U, or I'll just use this notation, U final, I'll just use my standard notation where the initial has a 0 subscript and final has no subscript. So if the spring was stretched from its starting from its unstretched condition, then U initial would just be 0 by assumption. We just assume that the potential energy is 0 when the spring is unstretched. And so delta U is just equal to U. So we could just write this equation as U is equal to half kx squared. So this equation tells us that if you stretch a spring by an amount x, then the change of potential energy of the spring is just going to be half kx squared. And you can also see that the same thing would happen if the spring were squeezed. So let's say that this is x equals 0, and you squeeze the spring down to somewhere over here, x equals some x over here where x is less than 0, right? So the change of potential energy would be exactly the same thing because the work done would be the same, as you can easily verify by just redoing that calculation. And so the change in potential energy would be exactly the same. So this equation here is telling us giving us the potential energy of a spring which has been stretched or squeezed by an amount x. So it will have half kx squared joules of potential energy. All right. The next, so that is spring potential energy. All right. Next thing that we're going to talk about is gravitational potential energy. So for every kind of every conservative force, there is a potential energy associated with it. So next one that we're going to talk about is gravitational potential energy. We can figure that out in exactly the same way as we calculated spring potential energy. So gravitational potential energy, and we've actually already done this. You've seen this many times before. So suppose you have this object over here on the ground. I'll just make this a point mass. Just keep it as simple as possible. You have a point mass sitting on the ground, right? Mass is m. All right. Suppose you lift the object up till here, right? What is the work done by gravity? So is gravity doing positive or negative work as you lift the object up? The answer is negative, right? Because gravity is pulling downwards, the object is moving upwards, so it's not getting its way. So what is the work done by the gravitational force? So gravitational force is constant. So the magnitude of the force is mg and direction is downwards. And let's say that the object has been lifted up by height h. All right. So what is the work done by gravity? So just you can just use the simple formula for work. We've done this many times. So it's going to be force multiplied by the distance multiplied by cosine of the angle between the force and the distance. And what is that? So the force is downwards, this displacement is upwards. So cosine of 180 degrees, which is -1. So the work done by the conservative force of gravity in this case is just going to be minus mgh, right? So now we can easily figure out the change of potential energy of the object. So delta U is going to be minus WC from the definition of potential energy. And so you can just plug in minus of minus mgh. What does that come to? It's going to be positive mgh. So you can see that the change of potential energy as an object is lifted through a height h is equal to mgh. And this is the formula for gravitational potential energy, right? All right. Now, there is one subtlety involved in this. Since the gravitational force is constant, uh, it does not matter where you choose h equals 0. So in this particular case, we chose h equals 0 on the ground, but there is absolutely no problem if you choose h equals 0 somewhere over here or over here or at the top over here. It doesn't really matter. You can choose h equals 0 wherever you want, right? Um, because as you can see, it's only the change in potential energy that is defined, that we care about. The actual value of the potential energy is meaningless by itself. You always have to have a reference level where you know that the potential energy is 0, and then you calculate potential energies relative to that reference level. So for gravity, you can choose the reference level where potential energy is 0 wherever you want. Um, However, for in the case of the spring, you have to choose the reference level. Since the spring force is not a constant force, you have to choose the u equals 0 at x equals 0, which is what we did in the previous example. So whenever x is equal to 0, we choose u equals 0 over there. And we don't have the freedom in the case of the spring force to choose the spring potential energy to be 0 at any other point. Whereas for gravity, you can choose h equals 0 and u equals 0. You can choose h equals 0, which automatically makes u equals 0. You can make this choice h equals 0 at any height you want. Though it's usually most convenient to choose h equals 0 at whatever is the lowest height in the problem, like the ground or something like that. All right, so we have covered the expressions for spring potential energy and gravitational potential energy, and these will be very, very important going forward. Okay, and hopefully it's clear to you that both of these are just applications of our very important equation right here. All right. Okay, one more definition. The sum of kinetic and potential energy is defined as the mechanical energy of the system, E mechanical. So mechanical energy is simply the sum of the kinetic energy, K, and potential energy, U, of the system, right? So that's just a definition. All right, so now we're going to define something very important. Uh, so we're going to derive this equation right here, and this is a very, very, very important equation. The equation at the top here is not showing up on the slide very well. Let's see if it shows up like that. It's not showing up here anyway. All right, so let us, okay, so let me just do this over here. All right. So suppose you have a system where maybe you have an inclined plane like this, and you have a box which is being pushed up by you. So you're exerting a force up on the box, right? And there's a bunch of other forces acting on the box as well. So there's mg acting down like this. There is the normal force acting like that. There is friction, maybe kinetic friction acting this way. So there's a bunch of different forces acting on the box, right? And the box moves from the bottom of the incline to the top of the incline, right? Okay, now you can calculate the work done by all of these forces, right? If you add up the work done by all the forces, then you get what we call the net work, right? And we know, just a review of what we've learned so far, that the net work on the system, which is the box, is equal to the change of kinetic energy of the system, right? Net work is what determines how much the kinetic energy of the system is going to change. All right, nothing new there. What we're going to do now is we are going to classify the different forces acting on the system into a couple of different categories. So we are going to have external forces, we are going to have non-conservative forces, and we are going to have conservative forces. So we are going to classify the various forces here into these three categories. All right. Now, what is an external force? An external force is simply a force that comes from outside, that originates from outside your system. So here our system is simply the box, right? So the force that's exerted by an external agent is what we call an external force. Actually, I'll just let me rephrase that. So the external force is defined as the force exerted by an external agent who's external to the system. So you are external to the system, right? So the force exerted by you on the system would be an external force. So F would be an external force, right? All right. What about friction? So friction is always friction, air resistance. These are always non-conservative forces. So the friction, the kinetic friction, would go in this category. What about mg? There are only two conservative forces that you see in all of physics 1, and those are gravity and the spring force. So gravity is clearly a conservative force, right? So we have classified the forces into these three categories. What about Fn? Why do you think I didn't take Fn into account? The answer is because Fn does not do any work over here. So the reason that we are considering the forces now is because we want to plug them into the into the network part of the work kinetic energy theorem. So we are only concerned with the forces that do work. Fn, and this should be clear to you by now, does not do any work. And can you tell me why Fn doesn't do any work? So pause the video and tell me why Fn doesn't do any work. The answer is because Fn is perpendicular to the displacement. The object is moving parallel to the incline, and Fn is perpendicular to the incline. And so Fn doesn't do any work in this case, and so we don't even need to consider it, right? So we have broken up our forces into three categories, right? Let's put that down. So we'll write the work kinetic energy theorem as, so W net equals delta K. And so we saw that we can break this W net into work done by an external force plus work done by non-conservative forces plus work done by conservative forces, right? That covers all the different types of forces that you have that are doing work, and that is equal to delta K, right? Okay, now I can do one more thing in this equation. I can use our very important relationship that we just learned, which is that the work done by conservative forces is related to the change of potential energy by this equation, which is the definition of potential energy. Let me use this equation to get rid of the WC And so then what you get is W external plus W non-conservative minus delta U is equal to delta K. And if I move the minus delta U to the other side, I get delta K plus delta U. And if you want, you can also write this as delta E mechanical, because you know that K plus U is equal to the mechanical energy. All right. So what we just saw is that, so okay, I might as well just write that. So delta E mechanical is equal to the work done by external forces plus the work done by non-conservative forces. So please make sure that you are absolutely clear up till this point. This equation was the first equation on the slide, which didn't show up very well. All right. So work done by external forces plus work done by non-conservative forces is equal to the change of mechanical energy of the system. Okay, so you can see now one consequence of this equation. So this is, by the way, this is called the equation of conservation of energy. Notice that it is not any different than the work kinetic energy theorem. The work kinetic energy theorem is also a statement of conservation of energy, but this equation just makes it a little bit easier to understand. But it's as far as the physics is concerned, it is identical to the work kinetic energy theorem, right? So what does this equation help us see? Suppose you have a situation where there is no external force acting on the system. So there is nobody actually pushing or pulling the system, or if the system happens to be a car, then the engine of the car is not running, right? If it's a sailboat, then there is no wind pushing on the sails of the sailboat. So suppose the external force is zero, and so the work done by external forces is zero. And let's also suppose that there is no non-conservative force acting on the system, which means that we are ignoring friction, air resistance, and all these non-conservative forces. What can I say about delta E mech? So this would imply that delta E mech, the net, and E mech is simply the sum of the kinetic and potential energies. Delta E mech is equal to zero. So that means E mech in that case would be equal to a constant. So if there is no external force acting on the system and the work done by external forces is zero, and also if there is no non-conservative force acting on the system, so there is no work done by friction or air resistance or any of that, we conclude that the mechanical energy of the system would be constant or conserved, right? So basically the equation of conservation of energy is just the statement that energy is always fully accounted for. Energy cannot show up from nowhere. Energy cannot disappear into, energy cannot just simply vanish. It's always fully accounted for. So if you have a system whose only energy is mechanical, so it only has kinetic energy and potential energy, then if there is no force, external force acting on the system, or if there is no friction or air resistance or any other kind of dissipative force like that, non-conservative force, then the mechanical energy will not change. And if you ever see that the mechanical energy is changing for a certain system, that simply means that there is work being done by either an external force or by non-conservative forces, or both, and that accounts for why the energy of the system is changing. So in other words, the energy, total energy of a system is completely accounted for. Right? So please make sure you understand that. And this is called the energy equation of conservation of energy. Now, there is another way of writing this equation, this one, which makes it a little bit easier. So this is something that I saw in your textbook, and I like that. So W external plus WNC is equal to delta E. So instead of delta E, I'm just going to write delta K plus delta U. And one thing that your book does is that it calls this, the sum of these two, as W other. I think it calls it, Yeah, so there's one thing that your book does, which is a little bit strange. It's not done by other books, which is that your book just considers the external force also as a non-conservative force. So your book calls this entire left side as W non-conservative, and you can do that if you want. It's just naming things. It doesn't really make that much of a difference. But it's more standard to make a separation between the external forces, which are forces applied by external agents, and non-conservative forces, which are the dissipative forces, friction, air resistance, and all that. So that's what I like to do. I like to keep those two separate. So anyway, so I'm going to call external forces and non-conservative forces as W other. So W other is equal to delta K plus delta U. That's just a rewriting of the equation that we had. Now let's do one more thing. So let's write delta K as delta of something always means final kinetic energy minus initial kinetic energy. Final minus initial is what the delta means. And you can do the same thing with U. So that's U final minus U initial. And that is W other. One last step. Let's move the initial quantities on the left to the left side of this equation. So that gives us K initial plus U initial plus W other equals K final plus U final. This is a very, very important equation. And this is just a rewriting of the same equation that we had earlier. But this equation makes it a lot easier to do problems. So please note that this equation is identical in content, identical in content to the work kinetic energy theorem, which was net work equals delta K. So these two equations are the same. The only reason that this equation is more useful is because it brings in the concept of potential energy, right? And so that makes it a little bit easier to calculate things using this equation. So all the problems in chapter 6 and chapter 7 can be easily solved using either one of these two boxed equations, right? I would say that it's a little bit easier to use the K0 plus U0 plus W other equals K plus U. And so when you're doing problems from chapter 6 and 7, you can use either one of these. Okay. All right, so I have this little tutorial which I created a while ago. If you're learning this subject for the first time, I would highly recommend working through this tutorial. So you would be using Newton's laws and kinematics for the first few parts. So it's a good review of chapters 1 through 5, which we covered in the first test. So please do this. And each of these is just like 2 or 3 lines of algebra to work these out. So I would highly recommend working through all the steps over here. And this equation, I mean, this exercise would help you numerically verify the equations that we just derived. The equation of WC is equal to minus delta U, and then the equation of conservation of energy. So you're going to actually plug in numbers and show that these equations are true. They indeed work. All right. So if you're learning this for the first time, I think it's a very good exercise to build up your conceptual understanding. And also, if you've seen this before but are a bit rusty, I would highly recommend working through this little tutorial. All right. So what we're going to do next is we will just discuss a bunch of example problems where you use the equation of conservation of energy that we just derived, right? So in some problems, you can use the equation of conservation of energy and you can get to the answer using just that. In some problems, in some other problems, more complicated problems, you might have to use the equation of conservation of energy, and you might also have to set up Newton's laws, and you might have to do both in order to get the answer. So we will see examples of both of these types of problems. In general, please remember that energy techniques are very, very powerful. And so if you're thinking of a way of doing a problem, try to use energy first, because if it's possible to do a problem using energy, then that is typically the easiest way to solve that problem. All right. So let's start with this example here. So what is this example saying? Please pause the video and read the problem and give it a try yourself as usual before you watch me solve it. Okay, so this problem is saying that, oops, there, okay. So this problem is saying that a ball of mass m, 2 kgs, is thrown vertically with a velocity v, v initial, that's given. So the velocity of the ball, initial velocity of the ball, v initial, is given. So the ball rises up to some height. And the question is, what height does it rise up to? This height is h. So we have to find this capital H, the height that the ball rises up to. Now, your first instinct might be to immediately reach for kinematics. We have actually solved this same exact equation when we were discussing kinematics. So you can certainly solve this problem using kinematics, but let's forget about kinematics for now, and let's try to use our new equation, k initial plus u initial plus w other equals k final plus u final. So let's try to apply this equation over here. All right. So the initial uh, point is when the object is launched from the bottom. Final point is when it reaches the top. So we've chosen our initial and final points, right? Let's calculate the initial kinetic energy, the kinetic energy at the initial point. So what is the kinetic energy at the initial point? It's just going to be 1/2 m v initial square, right? The v initial is given. What is the potential energy at the initial point? So in order to do that, you have to choose a zero level of potential energy. And as I said, choosing the ground to be your h equals 0 is absolutely fine. So let's do that. We'll choose h equals 0 on the ground. So what is the potential energy of the ball on the ground? The answer is 0 because there is no potential energy. mgh gives you 0 if h is equal to 0. In the first part of the problem, we have been asked to ignore air resistance. So what is W other? Let's remind ourselves what W other means. W other means work done by external forces and work done by non-conservative forces. So please make sure that you are clear about what W other is. W other is anything that's not a conservative force. And there are only two conservative forces in physics. One, gravity, and the spring force. So if you have any other force acting on the system, apart from gravity or the spring force, you need to take that into account under W other. So here, there is no external force, and we've been asked to ignore friction. So that means W other is 0. Okay, now let's get to the top position. So at the top position, what is the kinetic energy? So the object comes to a rest for a moment at the top position. So the kinetic energy is 0. What is the potential energy at the highest point? So the potential energy, according to the formula for potential energy, would just be mg capital H, right? And so we have our equation. So half mv0 square is equal to mgh. The m's cancel out, and so you can immediately solve for h, and that will be v0 square divided by 2g. And if you remember from chapter 2, that's exactly the answer that we get from kinematics. And you can see how easy it is over here. For kinematics, you have to set up sign conventions and choose an origin, then look at all the kinematic equations, figure out which one to use, and then plug things into the kinematic equations. Here, all we did was we wrote down the equation of conservation of energy, and in one step, we got the answer. Okay. So if you were to plug in the numbers here, you would find that h is equal to 5.10 meters if you were to work it out numerically. All right, let's look at the second part. What maximum height would the object reach if the air resistance force was 5 newtons? So the problem asks us to consider a simplified version of the air resistance force. We are pretending that the air resistance force is constant. In reality, it's not quite constant, but we are not going to bother with that here. So we're just going to consider the air resistance force to be constant, and uh, the value of the air resistance force is Fd, which is 5 newtons. So how do we do the problem now? So the object is being launched from over here, same setup. So the initial velocity is v0, and then it goes up to a maximum height, which is what we are looking for. So let's call the height again. I call the last one h. I'll just call this one h2. So we want to find out the h in this case. How high does it rise? So let's just start with our equation again. K initial plus U initial plus W other equals K final plus U final. Okay. Initial kinetic energy is half mv initial square. Initial potential energy is 0, just like the last problem. Is there a W other we need to consider? The answer is yes, because now there is a non-conservative force of friction, right? So we need to take that into account. What is the work done by the air resistance force? The answer is, let's calculate that. So as the object is rising up, it feels this constant air resistance force. What direction is the air resistance force going to be? Friction or air resistance will never aid the motion. So they're going to always be directed opposite the direction of the velocity. So air resistance force Fd will be in the downward direction on the way up. And on the way down, it's going to be in the upward direction. So friction will always oppose the velocity, oppose the motion. So it will always be directed opposite to the velocity. So as the object is rising through the height h, it's the work done by the drag force is going to be magnitude of the force, which is Fd, uh, magnitude of the displacement, which is h, and cosine of the angle between the force and the displacement, which is 180 degrees. And so cosine of 180 degrees, as you know, is minus 1. So this will be a negative work of magnitude Fd multiplied by h. Does it make sense that the work is negative? Yes, because the force is pointed downwards and the object is moving upwards. So the work is negative. Work is going to be negative. So, all right, so we are done with the left side of this equation. Let us put in the kinetic energy for kinetic and potential energy at the final point. So the kinetic energy would be 0 because it comes to a rest, and potential energy will be mgh. So now we can solve for h in this case, and so h would be what? So you would move the fdh to the other side, and so it would just be 1/2 mv initial square divided by fd plus mg would be the answer. So you know how high it's going to rise, and you can clearly see from here that the answer will be less than before, because you have a quantity, you have the denominator is larger. So if you plug in the numbers, you'll find that h in this case is 4.06 meters. All right, so we're done with the second part. Let's consider the third part. So in the third part is an extension of the second part. So the ball rose up to a height of 4.06 meters. And then what happened was that a spring was moved underneath the ball, right? So the spring was just placed over here. And let's say that the ball is made of metal, and the spring is also, the ball is magnetic, and the spring is also made of metal. And so when the ball hits the top of the spring, it's just going to stick there, right? All right. Actually, let's just imagine that there is some glue at the top of the spring, because if there's a magnetic force, that would change that would complicate things a little more. So let's just imagine that there is some glue or something on the spring, and so when the ball hits the spring, it's just going to stick there, right? So this is the initial situation. The ball is at the top, the spring is now brought in, and then the final situation is that the ball hits the top of the spring and sticks there and compresses the spring. So now the spring is compressed, and the spring and the ball, so the ball is over here now. The spring and the ball are at a lower height. I mean the ball, and this is where the ball basically stops, right? Compressing the spring. The question is asking how much will the spring compress before the ball stops, right? So initially, let's just make another coil of the spring. So initially the top of the spring was over here. The top of the spring was over here, right? And after the ball landed on top of the spring, uh, the top of the spring is over here. So the question is, how much does the spring compress before the ball comes to a stop? So how can we answer this question? Well, we can simply apply conservation of energy again. So K initial plus U initial plus W other equals K final plus U final, right? So in this, I typically like to use letters and work with letters until the very last step of a problem. But since uh, we have a lot of different heights and stuff here, it's probably easier if we just work with the numbers. So what was the kinetic energy, the initial kinetic energy of the ball at the top? The answer is 0 because the ball was at rest at the top, right? What was the initial potential energy of the ball at the top? So it starts from a height of 4.06 meters, which is the answer to the previous part. So the potential energy of the ball is mg times 4.06. Okay, there's one more thing that's given in the problem, which is that the ball, we are told that the ball comes to a stop 1 meter above the ground. That's also given in the problem. All right, okay, so back to our equation here. So U initial is mg 4.06. Is there a W other here? Yes, because we are told that air resistance acts the entire way, right? So air resistance acts on the ball all the way, the entire time that it's moving. What is the work done by air resistance? It's going to be negative work because this time the air resistance is going to point upwards. It always opposes the motion. So it's just going to be minus the drag force multiplied by the total distance that the object moves. How much distance did it move? It moved a distance of 4.06 minus 1, which is 3.06 meters. All right, so that is the W other. What is the final kinetic energy? The final kinetic energy is 0. What is the final potential energy? Now, there are two types of potential energy involved here because you've got gravity and you have the spring force. So both the gravitational force and the spring force are acting on the system. And so you have, in each of these conservative forces has potential energy associated with it. So you have to consider both types of potential energy. The gravitational potential energy of the ball, we've chosen H equals 0 again, like we did in the other parts of the problem. So the gravitational potential energy of the ball would just be mg times 1. And what about the spring potential energy of the ball? That is going to be, the formula for that is half kx squared. So 1 half k x squared. X is clearly the amount that the spring has been compressed. And you have an equation in which you know everything. You do know what m and g are and ft are. So you know everything in this equation. You also know what k is. So you can just solve for x from here. And that is the amount that the spring has compressed. All right. Okay, so we're going to do one more problem in this video, and that is this one. So okay, I'll let you read the problem. Okay, so feel free to pause the video and give this problem a try yourself, and then we are going to and then look at how I solve it. So what's happening in this problem is that there is a ramp and a truck starts at the bottom of the ramp, and that's when the driver slams on the brakes, and so the truck starts skidding at that from that point on, and then it just skids all the way some up till it gets to some height over here. Okay, you're given the coefficient of static friction and kinetic friction. The first thing that you need to figure out is that how far will the truck skid before it comes to a rest. So you have to find this height, this distance, d. That's what you have to find, right? Now, it's entirely possible to do this problem using Newton's laws, but that's not what we are going to do over here. So this could have very well been a problem on the first test. It's just an application of Newton's laws, and it's totally possible to do this problem using Newton's laws. How would you do it using Newton's laws? You would just consider all the forces that are acting on the track on its way up. So the forces, let's just draw the forces. So you have mg acting down, you have the normal force acting like this as usual, and you also have friction. So you have and what kind of friction would that be? Clearly it's kinetic friction. So these are the three forces acting on the truck as it is on its way up. You know the initial velocity of the truck, that's given. And so you can resolve these forces, and you can find the acceleration of the truck as it's going up the incline, right? And then you know the initial velocity, and you've just found the acceleration using Newton's second law. And from there you can find out the final velocity, how much distance will it cover as before it coming to a stop. So this is a very standard Newton's second law plus kinematics type of problem, but we are not going to use that approach. Okay, so we just need to do one little thing here. Since we've already set up the forces, we might as well just do one more step and break the forces into components. So you're going to have one component like this and another component like that. So you know that if this angle is theta, then this angle will be theta. And so this component, as usual, will be mg cosine theta, and this one will be mg sine theta. There's absolutely nothing new here at all. So this is all stuff that you've seen before, chapter 5. Okay. All right, and we can just discard the mg at this point. Okay. All right. There's one more thing we can do. Let's get, we know that from Newton's second law, if you apply Newton's second law in the perpendicular direction, then Fn minus mg cosine theta, F net in the direction perpendicular to the incline, that's Fn minus mg cosine theta, is equal to mass times acceleration. But do you have any acceleration in the perpendicular direction? The answer is no, and so that's going to be equal to 0. So in this case, you can see that Fn is equal to mg cosine theta. We can use this to get an expression for Fk. The formula for kinetic friction is mu k multiplied by Fn. Mu k is given, and for Fn I can just plug in mg cosine theta, and we are all set to use the new approach in order to solve this problem. So we just needed to set up Newton's second law to just get an expression for the friction force. Mu k Fk is equal to mu k times mg cosine theta. All right, so now what do we do? Let's start with our equation. Let's start with our equation. Can I move things? Let me see if I can move things. So I was just trying to make a little bit of room. No, I don't know. Anyway, never mind. Okay, so Yeah, I was just trying to move these three equations to the side or something so I can just work underneath this diagram, but that's all right. I can probably just still make it work. So actually, let me just do this. So the important thing that we just derived from here was Fk is equal to mu k times mg cosine theta. So just so I can continue to use this diagram, I'll just make a little bit of room here. All right, so let's start applying work in it, the equation of conservation of energy. So K initial plus U initial plus W other equals K final plus U final. All right. So so let's consider the bottom point to be the initial point and the top point to be the final point, right? What is the initial kinetic energy? It's just going to be half m v initial square. What is the initial potential energy? So we only have gravitational potential energy in this problem. If we choose h equals 0 at the bottom, then the initial potential energy will just be um, 0. So we don't have that. What about W other? So here we do have friction force which is doing work, right? So that is going to be, that is a non-conservative force. So we do need to take that into account under W other. So the work done by friction would be the magnitude of the friction force times the displacement. And so the displacement is the unknown quantity d that we are looking for. So times d times the angle between the friction force and the displacement. The displacement is from the bottom position to the top position. The friction force is always down the incline because it's opposing the motion. So the angle between them is 180 degrees, and cosine 180 degrees is -1. So I'm just going to write minus Fk multiplied by d. That's W other. Okay. Now, what about the final position? The final position, what's the kinetic energy? Kinetic energy is going to be 0 over there because it comes to a stop. And what about the potential energy? The potential energy would be H, mgh, where h is the height of the truck when it comes to a stop, right? What is the relationship between d and h? You can see that they're related. They form a right angle triangle. D is the hypotenuse of the right angle triangle. And so h is simply d sine theta, right? So h is just d sine theta. Okay, so let's plug that in, plug all this in, and we are done with the problem. So all I have to do is half mv v0 square minus, for fk, let's just plug in what we got earlier, mu k times mg cosine theta multiplied by d is equal to mg, and instead of h, I'm writing d sine theta. And now all I have to do is just solve for d, and amazingly, I'm done in like 2 lines of work. I'm already done. So d, the distance that the truck slides up the incline, is just going to be, just if you rearrange this equation, you're going to get 1/2 mv0 square divided by mu k times mg cosine theta plus mg sine theta. And you can see that the m also cancels out. So the answer doesn't depend on m. And that's the final answer. So as you can see, using Newton's second law and kinematics, that would have been quite tedious. But if you use conservation of energy, it's literally just 2 lines of work to get the answer. We had to do a little bit of work in the beginning to figure out the fact that Fk is equal to mu k times mg cosine theta. But once we figured that out, the rest of the problem was just very easy. So that's what I meant when I said that energy techniques are the most powerful and they make it easiest to solve certain problems. Okay, so we have pretty much covered uh, all the ideas in chapters 6 and 7. in these two videos. And oh, there's one more thing which I'll just very briefly mention, and that is the concept of power. Right, so power is, so we've been talking about uh, work. We have never considered how fast the work is being done, right? That quantity is measured by power. So power is simply the total, so you can have an average power and an instantaneous power, right? Like any rate that we've studied before. So the average power is simply defined as the work done divided by the time. So that's just average power. So if a certain force does 10 joules of work in 2 seconds, the average power over those 2 seconds would just be 5 joules per second, which is also called 5 watts, right? So that is average power. Sometimes it's more convenient to talk about the instantaneous power. I don't know why these equations are not showing up very well. So the instantaneous power is simply uh, same idea. You calculate the average power, but instead of calculating it over a large interval like 2 seconds, you can calculate it over a very tiny interval surrounding the point at which you want the instantaneous power. So if you want to calculate the instantaneous power at t equals 7 seconds, then you consider a very tiny interval, maybe from 6.99 to 7.01 seconds, and do the work done divided by that very tiny time interval. Just like we talked about instantaneous quantities back in chapter 2. So the limit where you make that time interval tend to 0 is the instantaneous rate. So that, as we know, just becomes the derivative. So the instantaneous power is simply the derivative of the work, dw dt. Okay. The unit of power, as I just said, is a watt. And another unit that's also used is the horsepower. 1 horsepower is 746 watts. So a horsepower is a unit that's been used for a very long time. I'm told that this unit came about because people, when cars were first becoming popular, horse-drawn carriages were the established thing at that time. So car manufacturers had to give potential customers a way of understanding how powerful the car's engine is. So they would say that this car's engine is equivalent to 2 horses or 3 horses, something like that. And so that is where the horsepower comes from, and it's just stuck around. Now, horsepower is just 746 watts. Okay, that's really all there is to power. There is one other equation which I will just very briefly mention here. The power is equal to the product of force times the velocity. So how do you see that? You can use either of these two definitions of power to see that. Let's just start with this one. So you can write so the work done over a tiny interval dr. Let's just do one dimension to keep things simple. So dw is equal to the force times the displacement. We're just going to consider work done in one dimension. So over a tiny little displacement dx, the work done by the force is given by f times dx, right? And so if the object moves over the direction over the displacement dx in time dt, then the power would just be dw divided by dt. So f times dx divided by dt. And so it's f dx divided by dt, as you know, is v. So it becomes f multiplied by v. And if the force and the displacement are not in the same direction, then this multiplication just becomes a dot product, as you can see over here. So this formula is also sometimes useful. Power is the dot product of the force and the velocity. So power is equal to f dot v. And in one dimension, it's just f multiplied by v, if the angle between them is the same. And so that's all there is to power. And all I'm going to do, all that we have left to do, and this is something we'll probably do in the next lecture, is just a couple of more examples of problems on this topic. Right?